Well, hello everybody, and welcome to Lecture 7 of our Calculus 1 course. Today we're going to talk about antiderivatives, which are the next major topic of our course and are the opposite of the derivative. Now, what do I mean by the opposite of the derivative? Well, okay, so let's consider a function y equals f, and the curve y equals f of x given by some function f of x. Now, this function is increasing exactly where the derivative is positive, and it's decreasing exactly where the derivative is negative. And so I'm saying this because now we're gonna try and graph y equals f prime of x. Something that plausibly could be y equals f prime of x. And in order to do this function is certainly, it's going to have to be positive where this is positive, it's going to have to be positive where this is increasing. It's going to have to be 0 when the tangent is horizontal, and it's going to have to be negative where the tangent has a negative slope, because this is nothing other than the slope of the tangent line. And some other properties it has to be increasing when this is concave up. It has to be decreasing when it's concave down, as we know from second derivative business. So let's see, it's going to be concave down over in here, concave up over in here, and then concave down again until about here. So, okay, so positive when this is increasing, so it's going to be positive up to this point, but it's positive and decreasing because it's concave down. So it's going to be, and then it's going to be 0 right here, so it's going to be something like this, and then so now it goes negative, and it's still concave down, so it's negative and decreasing until we get to here, and then it's still negative, but it starts increasing because now we're concave up. And it's 0 right here where we have the horizontal tangent. So we'll actually a little further over. Horizontal tangent. And then it's increasing where it's concave up, positive, increasing up to this point. And then at this point it's concave down, and it begins decreasing again. And then right here it hits 0, and it's negative, but it's still concave down, so it's decreasing and decreasing, but it's decreasing up to this point, and then at this point it is concave up, roughly. It seems to be concave up, so it's increasing, but of course the tangent is still negative, and it's flattening out, so it goes towards 0. Perhaps it's an asymptote, who knows? Okay. So there's a little review of concave up and concave down, and we've graphed the derivative of this function. But we may ask, if we're given a curve y equals, let's call this y equals g of x, how do we go backwards? So let's try going backwards actually from this curve. And why did I throw g in there? Throw g in the mix. Actually, let's use g to denote something else. To denote this other function. So let's say that g of x is a function with g prime of x equals f of x. Okay, so this is a function which is going to need to be increasing whenever this function is positive, and it's going to need to have a horizontal tangent whenever this function is 0. This function is only 0 right here. And it's going to need to be decreasing whenever this function is negative, which isn't any time. It's not negative any time. So that sort of seems perhaps like we don't have much to go off. But we also know that whenever this function is increasing, it has to be concave up. Whenever this function is decreasing, it has to be concave down. So that's a little bit to go off. So horizontal tangent right here because it's 0, and then concave up. Well, this is increasing, so concave up to this point. And then when this goes to 0, that means we're going to have an inflection point. I should draw this a little bit further down so we can really do it. It should have an inflection point. And it's interesting to note that if you think about it, it doesn't really matter what the value is over here. We can just move it down and it doesn't change what's going on with the derivative, which more on that later. But so it's concave up where this function's increasing, and it's increasing wherever this function, this is concave up wherever this is increasing, and so this is y equals g of x that has this property, and this is concave up wherever this is increasing, and it's increasing wherever this is positive, just to reiterate. So we get to this point, an inflection point, and it's, so for critical point of the derivative is going to be an inflection point of this function g, which has f of x as its derivative. So here we have an inflection point, so it becomes concave down, but still increasing, and still increasing but concave down until this point is some higher thing that doesn't matter for our purposes. It's still concave down because this function is decreasing until we get to this point, and then this function is increasing, so it again becomes concave up, and then here this is going to be another inflection point. It's going to become concave down as it's decreasing but still positive, and we have this concave down. It's still increasing. So, okay, so that's just a flavor of how we could sketch something that could plausibly be a function g of x that has g prime of x equals f of x. And that's really what antiderivative means. Antiderivative means that the derivative of this function is f of x. So we say this right here, this is the definition of g being the antiderivative of f. So this here, this is by definition g is the antiderivative of f. So if f is the derivative of g, then g is the antiderivative of f. So it's the opposite of being the derivative. It's the antiderivative. Anti-derivative of f. So that's the definition of the antiderivative, viewed from one direction. And okay, so that was sort of an abstract curve, but maybe it would be helpful to consider something a little bit more concrete to see this picture. So say f of x equals something we're quite familiar with. Y equals f of x equals sine of x. Then, well, what's a function with sine of x as its derivative? Well, the derivative of cosine x is negative sine of x. So that would mean that the derivative of negative cosine x is negative negative sine of x, which is sine of x. So if we have g of x equals negative cosine of x, then this is going to be an antiderivative. This is y-axis, this is the x-axis. This is going to be an antiderivative of, I'll put the axes in the same place. This is going to be an antiderivative of y equals fx equals sine of x. So let me make sure that I draw this correctly. Relation to this. And all the things I said before should hold. So, because f here is the derivative of g, sine is the derivative of negative cosine, this has horizontal tangents exactly when this is 0. This should correspond to this one. 0. And horizontal tangent whenever this is 0. And this is concave down whenever this is decreasing, right? So this is decreasing here, which is exactly, if I turn it on it really well, correspond exactly to where this one's concave down. So this is concave down here, this is decreasing here, this is increasing here. And this is concave up right here where that one's increasing. So here's a sort of Cartesian coordinates graphing view of the antiderivative. So the antiderivative is going to be the function whose the antiderivative g of x here, we call g prime of x equals f of x. It's going to be the function whose slope, that has the slope of its tangent line at a given point, is the value of this function at this point. So that's one perspective on antiderivatives that is fairly in keeping with the conversations that we've had so far about derivatives and slopes of tangent lines, and doesn't really introduce any super weird or foreign, new, surprising concepts, but I'm actually about to do just that and introduce some new, weird, foreign, surprising concepts. Perhaps, unless you've already taken this class, then it will also be familiar. So let's do this. So, okay, so let's say that we have a curve. It's often how these conversations start. You have a curve, y equals f of x. Y-axis is the x-axis. And so let's consider a strange sort of situation where we don't actually know what f of x is. But what am I going to say we do know? In this case, I'm going to say that we do know the value of a different function, which is a of x, which is going to be the area under the curve in a certain region, and I'll shade in that region presently. So let's say, let's call this point x, or let's call it x0 rather. So at this point x0, let's say this region between the y-axis and the line x equals x0. The area within this region, say this is a of x. It's a of x. Is that really visible? Maybe I'll use blue, complementary color, yellow. So this is a of x. Is that visible? Yeah, that's pretty visible. So the area function, so we know what this function is that gives the area at a given point x. So then if we were to have point x1 right here, it would be this area plus this area that I'm going to shade in red up to this point. These red dashed lines indicate the fact that this region is also this area is also counted in a of x1. So sorry, I didn't say, this is a of x0, and then all of this together is going to be a of x1. So, okay, so we have this function. Of course, this is a foreign concept, perhaps, but and it seems strange why we're doing this. We'll get there. So we have this function a of x, which is the area under this curve up to a certain point, and this little red region right here, we can give an expression for this region, which is this region. If you think about it, you don't have to think that hard. This is a of x1 minus a of x0. That's the area of this red region. And okay, so let's say, what if this region were smaller? What if x1 were closer to x0? Which is going to be crucial to the next point I'm trying to make. Maybe I should have made the point and then make it small, but we're doing it this way, so whatever. So, okay, so let's say we have x1 now pretty close to x0. Then, as it gets close, this thing, of course, this is not quite a rectangle. This region with this area, it's not quite a rectangle, but getting closer, it becomes quite close to a rectangle. And in fact, the average value, and this is maybe a definition of average value, but it's a highly sensible definition. The average value of f of x, the average value of f of x along within this region, this red region right here, which has area a of x1 minus a of x0, is going to be the area of this region divided by the width of the region. So if it were a perfect rectangle, it would just be the height of the rectangle, right? And this basically is a perfect rectangle, so it basically is the height. It basically is f of x, or f of x0, f of x1. It's basically that, but it's the average value between x0 and x1, which why I would call it the average value. If you think about it, it makes sense. It's kind of a definition of the average value, but it's a definition which is in keeping of any version of average that we can really think of. Well, actually, there are a lot of definitions of average that we can think of, but it's the mean. It's the mean value. If you've ever heard of mean, it's not the median, but it's the mean. So I shouldn't say any version of average. Yeah, median would be another version of average you can think of. But so the mean value of f of x in the region x0 less than x less than x1, the mean value is going to be a of x1 minus a of x0, the area, divided by x1 minus x0. Now this right here is none other than the slope of the secant line of a graph y equals a of x. If we were to graph that in Cartesian coordinates and interpret y equals a of x as a curve, this would be the slope of the secant line. And it also is approximately equal to f of x1. Because of course, f of x is not changing, or sorry, f of x0, actually really both, but f of x0 we're interested in. So this is the mean value of f of x in this little region, and as x1 gets closer and closer to x0, this gets closer and closer to being a rectangle, and this mean value gets closer and closer to just being f of x0. So remember the quirky parameter that I put on the problem in the beginning, which is that we don't even know actually what f is, but we just know what a is, and so now this is giving us the ability to describe f in terms of a, which is good because I said that we didn't know what f was to begin with, but we did know what a is. So, and in fact, since it's going to get more and more accurate as x1 gets closer and closer to x0, we can go ahead and and go out on a limb perhaps, but it's a limb that we can go out on, it's going to be legitimate, say that f of x, in this limb that we're going out on, of course it could be proven more rigorously. There's probably a at least vaguely rigorous proof of this in your calculus textbook that you could read if you want. I think this proof is relatively rigorous, or at least relatively easy to make more rigorous if you wanted to. But anyways, so the point that I'm building up to is f of x0 equals limit as x1 approaches x0 of a of x1 minus a of x0. I should write this down a line, in fact. See that right there? Yeah, you should be able to see it. Limit x1 approaches x0 of a of x1. Oh, please excuse the crashing of objects. A of x1 minus a of x0 all over x1 minus x0. And this limit is, of course, the derivative of a of x at the point x0. So this, which, if you don't remember this definition of the derivative, just try doing the substitution h equals x1 minus x0, and you can rearrange all of this into your more familiar form of the derivative. The denominator, of course, becomes h. A of x1 becomes a of x0 plus h, and voila, derivative. So this equals a prime of x0. Okay, so in terms of what I was saying before, what does this say about the antiderivative? Well, it gives us a new interpretation of the antiderivative. And this is something I really appreciate about math, which maybe some people don't care about as much, but I strongly appreciate about it, is all the different ways of interpreting the same things. And it's truly the fact that mathematics has this property that you have this logical sequence of facts, which is fairly uncontestable, and that's perhaps an understatement, that this uncontestable sequence of statements in logic that in this mathematical language has to be true, but can be interpreted all sorts of different ways. And so, for example, that's why people argue about whether we live in a multiverse, or whether any fact is determined before it's observed or not, or whether that's one possibility or the multiverse is another possibility. And there are various other proposed possibilities, some more bizarre than others, well, actually all of them are bizarre, but some of them are more easily understandable than others, like the multiverse, everything is happening in parallel, is extremely bizarre, but at least it can be fairly well communicated, as opposed to like the guide wave interpretation of quantum mechanics, which says that everything is also, so the ultimate nature of physical reality via quantum mechanics that's widely accepted. The guide wave theory would say that everything happens whether or not it's observed, but it happens in this separate domain that is very strange. And the point of this is that quantum mechanics is based on mathematics, and it's built on uncontestable mathematical facts that don't have a single interpretation. So classical mechanics has the ultimate nature of physical reality that was believed in for many years, following Newton, our hero Newton, has a fairly, commonsensical sort of explanation that I think actually is what most of us tend to think of as the way things work, about, bumping into objects knocking into each other, and everything being determined, and there being a fact of the matter about the state of physical affairs. But quantum mechanics, you get into some mathematical theories that are a little bit more obscure in terms of their interpretation, and so, forgetting going beyond the physical, purely within the physical, describing the physical reality, there's a huge argument in interpretation. And so anyways, that little digression on the ultimate nature of reality, my point is that it's something I very much enjoy about mathematics, that you can interpret things in a lot of different ways. And what does that have to do with what we're talking about? Oh yeah, so interpreting the antiderivative either as the area under the curve, as we're doing now, or interpreting it as this function whose slope corresponds to the value of the original function of which we're taking the antiderivative. So moving on, let's look at a concrete example, which will be a little bit familiar going back to the first day. I threw a lot of stuff out there on the first day. And let's look at a concrete example that's based on an example I threw out on the first day of a concrete area problem, which at first appears slightly different than this, but which I will interpret and slightly alter into being an instance of this problem. So remember when I spoke of a square with length x, I think I called it L, but now let's call it x. The length of this square is x, and the area of the square is x squared. Now, so this is in some ways, this interpretation or representation of the function f of x equals x squared, or you can call it a of x equals x squared, area for side length x equals a of x squared. This is somehow fundamentally different than Cartesian coordinates. But let's alter the problem slightly, say of x squared over 2, and this allows us to do something kind of nifty, where we cut this in half, and let's call this the y-axis. Call this the x-axis, which makes sense. We're already labeling x to be this length here. So this right here, let's call this x0, and this area right here is a of x0, which is clearly half the area of a square. It's clearly half the area of a square, because we've just taken the square and we've cut it in half. But it's also the area under the curve y equals x. So here, y equals f of x equals x. And, of course, what I just showed you before was that a prime of x should equal f of x, so a prime of x should equal x. And, of course, now we can play that out and see that sure enough, a prime of x equals x. So I've not been misleading you. It's really what happens, at least in this case, and in fact in all sorts of other cases, I'll just say all cases, with the qualification that if you ever take advanced math classes, the right types of advanced math classes, you'll learn about some very strange cases where it's not true. But all normal cases, all cases that you can probably think of, that I can think of, is true. And yeah, so there's one very straightforward example, an even more straightforward example. Now, I didn't start with this example because sometimes simplicity, as we've talked about before, sometimes, and as I think has been observed by many of you, that sometimes simplicity actually makes things harder in mathematics. There's less to wrap your head around. But let's take a very, very simple case, which the curve is going to be y equals f of x equals 1. It's just a constant function. And then the area under this curve up to the point x1 is a rectangle with height 1 and base x0. So a of x0, blue, a of x0 equals 1 times x0, which is just x0. And of course, so a of x0, or a of x equals x. So of course, a prime of x equals 1. That's f of x, just like I said. So there are a few shallow end sort of examples, and of course, with any of the functions that we know what they are the derivative of, we can get some more interesting examples. So, like for example, let's, the next example I wanted to give you was 1 over x. So 1 over x is going to introduce a little nuance to our considerations that will be important. So remember, y equals 1 over x. If we wanted to graph it, okay, let's go here to 1/2. It's going to be about 2. 1/4 is going to be about 4. And then over here at 2, x equals 2, y is going to be about 1/2. X equals 4, y is going to be about 1/4. Then we have a curve. Connect the dots. We have a curve. So we want the area under this curve, and the area under this curve is going to be, so this is y equals f of x equals 1 over x, and this is, of course, the derivative of the natural log ln x. So this area, the area up to this point, x0, we fill in the area here. It's going to be something like the natural log of x, right? Well, okay, so what if that were the case? Then, as we went over here, that would mean the area back here as x, that would mean, so if so does a of x0 equals question mark, does it equal log, or natural log, ln of x? Now if it did, or of x0, if it did, then that would mean, so the limit as x0 approaches 0 of ln of x0 is, of course, negative infinity. And you can see by looking at the graph, you can see by considering how it's the inverse function as as x goes to negative infinity, e to the x goes to 0, and so then for the inverse function it's going to be the opposite sort of situation. So this is no good. I mean, we can't really talk about infinite areas, so that's no good. So this introduces a little nuance to our whole conversation, which is that the area that we're considering needs to be qualified a little bit. And the area is going to have to be counted from some horizontal line, which doesn't have to be, and in this case can't be, the y-axis. So I oversimplified things slightly when I said that it was going to be the area between the y-axis and under the curve up to some point. So in fact, and I'm going to propose that we now have the line from which it's measured be 1, x equals 1. So can we just do that? Well, actually we can, and let's see why. So I mentioned before that we could add a constant and nothing would happen. So what do I mean by that? So if a prime, or well, let's just go back to calling it g and set aside the idea of area for a second. But it of course applies to area too, which is the point. So say that g prime of x equals f of x. Then g of x plus 1 derivative also equals f of x. And this could actually be any constant. It could be 2, it could be 3, it could be pi, it could be the square root of 2. So actually any constant, let's call it constant c. That's what's quite customary in terms of integration, is to call that c. So g of x plus c, its derivative, equals f of x. And so the antiderivative is the same if you add constant values. And then if you go back to all the arguments that we applied before, and this is maybe the real justification, if we go back to all the arguments we applied before, it doesn't make any difference where the area starts. And so we could have the area start somewhere else, and that would just involve adding a constant value. And I'll do that at the end of this example. I'll change the starting point. But for now, let's use 1 as our starting point. And there's, of course, there's going to be nothing wrong with that. I assert, and hopefully you're convinced. So ln of 1 equals 0. And that's sort of why I chose that as the starting point. So this area right here, let's call this, so this is x0. So a of x0 equals ln of x0 minus ln of 1, minus ln of 1. And why ln of 1? Well, because a of x0 differs by ln of x0 by some constant, and it is, of course, the area of a rectangle that starts at 1 and ends at 1 is going to be 0. It's called a degenerate rectangle because it's not even a rectangle anymore. It's just a straight line. And so that means we need, if we plug in x0 equals 1, we need to get 0. But in fact, ln of 1, as I mentioned, is x0. So sure enough, a of x0, the area of this rectangle starting at 1 and then going over, is just going to be ln of x0. So yeah, so that's that. So for example, say that we have, to make this quite concrete, so this is 2, and this would be 3, and then right around here, we're going to have x0 equals e. So this area right here, this area underneath the curve y equals 1 over x, between x equals, isn't a very good e, between x equals 1 and x equals e, the area of this curve, a of e, is just going to equal the natural log of e, which is, of course, none other than 1. So, of course, if you wanted to, this is another way of interpreting what e is, if you like this interpretation. I mean, with these numbers, these transcendental numbers, pi has a good interpretation, but transcendental number like e, it seems like it might be nice to have a whole arsenal of interpretations of what e is, and here's one interpretation if you like it. It's the point so that the area of this under the curve here is 1. Has several other interpretations that you can understand if you were to study, for example, probability, discrete probability, the matching problem. But anyways, that's quite an aside. That's an interpretation of E, and so this if we have this situation where y equals f of x is some curve, and we have some starting point wherever, and we have this function a of x, so that this area from this dotted line, whatever it is, up to x is a of x. Then, and so this is recall, as I've been saying over and over again, a prime of x equals f of x. So the notation that's used for this is a of x equals, do this s, and let's say this point right here is called lowercase a. It's sort of a customary letter to use. So a of x is integral from a up to x, moving along from a up to x of f of We don't use x because we're using x here, sort of like with the derivative when we're drawing tangent lines. X0 is really another form of x, but we need another letter, and so we're going to use another letter here in the same way to denote something along the way, and oftentimes the letter t is used. Of course, it's sort of a loaded term because it's time, so I'm just going to use v. So f of v dv. Now this is Leibniz's notation, and why this notation, you may ask. And so this s is short for summa, which is Latin for sum, and this dv seems sort of enigmatic, and I'm going to attempt to explain both of those choices of notation, not notation, it's not from Newton, it's from Leibniz. These choices of notation, and what it comes from is, like I said, Leibniz was really into infinitesimals. So Leibniz imagined this area being the area under the curve being divided into these infinitesimally small rectangles. And the infinitesimally small width is dv, has width dv, the change in v, and has height f of v. F of v is the height. So s, summa, so summing up these little rectangles that have height f of v and width dv. So this is a product, f of v the height, dv the width. It's interpreted as a product, and s for summa, adding up the rectangles. Of course, there aren't actually any rectangles if you don't believe in infinitesimals. Of course, Leibniz did believe in infinitesimals, so he imagined it this way, and there's just something quite pleasing about this notation, and so we continue to use it. And of course, you can approximate it with rectangles in a similar way. It's actually quite analogous to the idea of approximating, it's different, but it's somewhat analogous to the idea of approximating the tangent line using secant lines. So you can approximate this area with rectangles in this way. And, but the dv, this is not really a width of a rectangle unless you believe in infinitesimals, because it's infinitesimally small width if it is a width at all. But we're not going to regard it as a width. We're going to regard it as Leibniz came up with this notation. It's kind of like an earworm, only more of a mind worm. There's just something about it that sticks, and so we stick with it. And there's something hypnotic about it and mesmerizing. I don't know if you feel mesmerized by this notation, but before I ever took calculus, it was one of the reasons I felt like I had to take calculus, is I saw these symbols and I just thought, I have to know what that means. There's something really beautiful about it. I don't know. That's my take on it. Of course, you might not feel the same way as I do, because I think most of you are environmental science majors, and I'm a math major, so maybe that's more my thing. I feel that way. But yeah, so there we go. So that explains the notation, and let's just talk some examples. And one important example, there's another little piece of interpretation that I've not given you yet, that maybe some of you have been thinking already. And this piece of interpretation is, what about negative values? We've been talking about area under the curve, but what about when we go over? Or sorry, when the curve goes under the y-axis. And this is easily seen in this most simple case of y equals x. So with y equals x, and remember I said that we could start our horizontal line anywhere we wanted to. So let's say start it right here. Well, what does that mean? So now we're going to want, and the way I'm saying that we're going to interpret that is going from here. So let's say this here is x, so we want a of x. And the way we're going to interpret this, and as I said in the last lecture, the negative numbers throw a bit of I won't say they throw a wrench into it, but they complicate a lot of things, and the way that they're interpreted seems sort of artificial oftentimes, which is why people refer to them as fictitious numbers for a long time. But the way that we interpret this is we consider this area to be negative, and we consider this area to be positive. And so we subtract this area from this area. So let's call this value x equals a. So this area under the curve here, a of x, we interpret to be the positive area minus the negative area. It's going to be x squared over 2 minus a squared over 2. The area of this negative triangle is a squared over 2, and the area of this positive triangle is x squared over 2. So we get the positive area minus the negative area. And if it was another curve that wasn't a straight line anymore, wasn't a plain old triangle, it was as Newton calls it, a curvilinear triangle, then the interpretation would be exactly the same, only this would no longer be x squared. It would be whatever the integral is of this strange function, like f of x. Yeah. So this would be, some other thing. It would be, we could write it integral a up to x of f of x. And similarly, we could move x in the other direction. So we could have, say, x over here. And this is a little weird, and what I'm about to say we'll revisit a little bit, so it's going to seem a little weird at first. But the way it's defined here is to make the formulas hold, which is one aspect of math that sort of frustrates me sometimes, is that things are defined in such a way that the formula holds. But so this is defined in such a way that the formula holds. So now I said I've always been talking about the x being to the right of a, but now x is to the left of a. Well, how do we interpret this? Well, and let me go back to the straight line example so that we have explicit expressions. So y equals x. This is just going to be x squared over 2 minus a squared over 2. So this area is now going to be a positive area. So, and that interpretation comes directly from this formula, because x squared is greater than a squared, because x is more negative than a is. And of course you square a negative and you get a positive. So this area is positive, and that comes from the fact that we move to the left instead of moving to the right. And so conversely, say a were to be little a were to be a positive number, and then if we went to the left, had x right here, then going to the left with the positives is initially positive, seems at first glance to be positive. Now it's going to be regarded as negative, and that can be seen because we insist that this formula hold. Well, x squared now is smaller than a squared, so this is going to be a negative area. It's a negative area because x is to the left of a. So let's see. So before going on, to more notation and a bit of a summary, before doing that, I want to give a few more examples. So, so here's sort of a definition or notation. So let's say we have f of x, and it's somewhat customary to say, somewhat customary but doesn't count full-fledged as notation. So oftentimes what you use is capital F to denote the function, a function, as I mentioned with the constants. It doesn't have to be a single, there could be multiple functions with this property, but So f of x is going to be some function, so that capital F of x is going to be some function, so that capital F prime, the derivative of f of capital F is little f. And to summarize what I have been saying about the area is a of x equals f of x minus f of a, where a is whatever the point is that we start at. So this is a function, a is the point we start at. So this is x, area between x equals a and x. So let's do some examples, and I'm not going to accompany every example with a picture because that, of course, would slow down how many examples we get through and computations. I guess I just want to hurry up and throw some computations out there. So some examples. We've already seen a few, and we could deduce all sorts of them just from the differentiation rules that we know. So say a equals 0, then we want to know what the integral from 0 up to x of 1 over the square root of 1 plus x squared dx is. Oh, sorry, I shouldn't use x, I'll use v. 1 plus v squared dv is. And if you want to accompany this with a drawing, that would be a good sort of work along exercise. But this may seem perplexing at first. Well, where do we start? Well, we kind of start at the end, which is this is the derivative of something. What is it the derivative of? It's the derivative of arctangent x. So f of x minus f of a, but a is 0. So this right here, this whole term is going to be what I've been calling a of x, area under the curve from 0 to x. So whatever, I'll draw a picture just to emphasize, keep the whole conversation grounded. So arctangent, of course, goes from negative pi over 2 up to pi over 2. So say this is our x value. This is going to be the area from 0 to x. So a of x. It's going to be arctangent of x minus arctangent of 0. But arctangent of 0 is just 0. So this area, a of x, equals arctangent. Oh, I'm sorry, I graphed the wrong function. I should be graphing 1 y equals 1 over 1 plus x squared. I went to the wrong level, so I apologize to anyone who paused and was thinking, what on earth is he doing? So this function is going to be more like something like this. Sorry, something like this. And why does this function look like that? You could think it through if you want. You could use do all the tests you have for graphing functions, or you could put it into Desmos. But that's what this function looks like. So the area so this is a of x. This area, and in fact, a of x equals arctangent of x. So yeah, any of us can fall prey to confusing which functions are which. Even I have been studying this stuff for 6 years. So yeah, be careful and don't be hard on yourself if you do confuse them. I'm sure you won't be hard on yourself, but yeah. So so this is this function is y equals 1 over 1 plus x squared, which we have been calling f of x, little f of x, And then in this case, arctangent of x is big F of x. And well, graphing I'm calling it x, but then in the integral I call it v. So there's an example with the graph, and now I'm actually going to do what I said, which is give some more examples that I won't necessarily give graphs, but so let's say integral x cubed dv, integral from 2 up to x. So we need something which has derivative v cubed, or derivative x cubed, because we're going to express it in terms of x. So we want to know what this is. This is going to be f of x minus f of 2, where f is some function such that f prime of x equals x cubed. Well, if you sat down and thought about it for a second, you could see that it's going to be some constant multiple of x to the fourth, right? Because the derivative of x to the fourth is x cubed. Of course, it could differ by a constant from that, but we'll forget about that for the time being. So the derivative of x to the fourth is x cubed, so the derivative of x to the fourth over 4, the derivative of x to the fourth is 4x cubed. So the derivative of x to the fourth over 4 is x cubed. So f of x, we can have f of x equals x to the fourth. Of course, it can actually be, x to the fourth over 4. It can actually be x to the fourth over 4 plus any constant, as I have been continuing to say. So you could say, well, what? If we can add any constant, how does the area make any sense? It could be anything. You just add a constant to it, which wouldn't make any sense. But, so if this here is x to the fourth over 4 plus a constant, so f of x, capital F of x minus f of 2, this is going to be 2 to the fourth over 4 plus a constant. Well, the constants cancel. So that's why, the constants make no difference. The constants added to capital F of x. So that's good. So it all checks out. So this is just going to be x to the fourth x to the fourth over 4 minus 2 to the fourth over 4, and 2 to the fourth over 4 is x to the fourth over 4. Well, 2 to the 4 is 16, right? 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16. And then 16 divided by 4 is 4, so we have x to the fourth minus 4. So this integral is x to the fourth over 4 minus 4. And so say x equals, let's say 3. If x equals 3, then let's call it a of x. Then a of x equals 3 to the fourth, and 3 to the fourth is 81, right? 3 is 3 to the 1, 3 to the 2 is 9, 3 to the 3 is 27, 3 to the fourth is 27 times 3, which is 81. So we're going to have 81 over 4 minus 4. Of course, we could undo what we did here if we wanted to have it all over a common denominator. 81 minus 16 is 65, so 65 over 4. So there we go. And of course, there's going to be plenty of examples of this, homework, all over the place. This is a thing that you can just do all day, kind of like taking derivatives. I've tried to de-emphasize in this class. I've tried to de-emphasize routine and repetitive work. I mean, I guess repetitive work, even repetitive work has its place. So I'll post some practice problems with some repetitive work, but of course it's sort of a useless way to evaluate, because for purely online class, because you can just look up all the answers to these sort of repetitive problems. Yeah, so now I'm going to introduce a little bit of notation, which my personal feeling is that is sort of useless, and so I've presented it in a different way, but I will use this notation because it's, whether or not I find it useful, it is universal, and so it's important to know, and we'll use it because it's so universal, and it's will be in the textbook. There's this distinction made between definite integrals and indefinite integrals, and so I guess it's sort of useful because you can talk about things more on the fly with the indefinite integral. And so indefinite integral. So an indefinite integral, Yeah, I mean, I shouldn't say that I think it's useless. It's solid. So indefinite integral is basically what we've been calling capital F of x. So capital F of x, I've been calling it, but it's more of an ad hoc notation. So the way that it's written is, and I'll give an example, would be that, like, indefinite integral sine of x dx equals negative cosine of x. And if you notice, I'm not distinguishing between x in the integral and x outside of the integral anymore, and I'm not putting any bounds on the integral, so that's what an indefinite integral is. So in the language that I was using before, the indefinite integral f of x dx is capital F of x, and for completeness, I will again say f prime of capital X equals f of x. So this is the indefinite integral, and then the definite integral. The definite integral is where we consider the bounds to be concrete. So, for example, if we had, say, integral 0 to pi over 4 of secant x dx. So notice I'm not using x in these bounds anymore, so we might as well use x inside of the integral. We just can't be using something in the bounds, and also this is sometimes called a dummy variable because you're summing it up. It's a variable that's being swept over as we move along and take the area under the curve. So it's fundamentally different. It's a fundamentally different beast than what is in the bounds because it's being swept over, as they say. So integral of secant squared dx. So you might be thinking, wait a minute, secant squared x, well, how on earth are we going to evaluate that? Well, we're going to evaluate it because we know that it's the derivative of something, which is exactly the key point of everything that we're talking about here. So this is going to be tangent. So the indefinite integral of secant squared x is tangent. So this is going to be tangent of pi over 4 minus tangent of 0. And of course, we know what these things are. Tangent of pi over 4 is 1. The slope of a triangle with angle pi over 4, that is angle 45 degrees. So that's going to be 1. And then tangent of 0, the slope of a degenerate triangle, which is just flat. So that's going to be 0. It's just 1. So this whole fancy expression is just 1. How about that? So this is an example of a definite integral. You plug in numbers to both these things. So concrete, the definite integral is more concrete, but yet mathematicians like to be abstract, and so even though this is concrete, oftentimes the concrete numbers will be denoted by an A and a B. And then, so with the capital F notation I've used before, and by the way, this capital F notation is not necessarily very versatile because functions could be named in all sorts of ways that would make it unnatural. But but in our present conversation, we're going to keep using it, but it's not this capital X. Capitalizing the letter for a function does not universally mean that it's the indefinite integral of that function, but in this case it is. So this is going to be f of b minus f of a. And so this is, I am not sure if I've used the word fundamental theorem of calculus yet in this lecture, and yet I've been stating and applying the fundamental theorem of calculus since, maybe 5 or 10 minutes into this lecture. So this is one statement of the fundamental theorem of calculus. Fundamental. The fundamental theorem of calculus. And why is it called fundamental? Aren't there other things I've been saying are fundamental? Well, yes, but the other things I've been saying are fundamental for the differential calculus. And now we're beginning to talk about the integral calculus. And the fundamental theorem of calculus relates the integral calculus to the differential calculus. And it relates it through the statement that capital F prime of x equals f of x. So integral is related to derivative. So, and then I said that, maybe it would become more clear why the integral is called the integral, why it's called integration. And maybe it is becoming more clear. I mean, you can think of all the values come into play, so it's integration, they're all integrated. I mean, if you like that. I don't know if the word necessarily corresponds well to a common sense version of the word integration, but you can think of it, it integrates everything. All the values here are being integrated into the value that we have as the area under the curve, I guess. I guess that makes sense of why it's called integrate. Or maybe it just, I don't know, it's up to you whether or not you care for that explanation. I mean, in mathematics, sometimes things get names that don't have the most natural interpretation, but maybe integral is good, maybe it's not. It's up to you to decide how you feel about that. So, in the rest of our time here, I will state a few directions we can go in terms of evaluating integrals of functions that are built out of functions that we already know. So remember, with derivatives, as soon as we started talking about derivatives, it became desirable to talk about the derivatives of functions built out from other functions. So first we had the addition rule, the constant multiplication rule, and then we had the product rule and the quotient rule and the chain rule. And so for integration, we're going to have corresponding rules for all those things, except the quotient rule. There isn't really a natural corresponding rule. I mean, you could make one, but it wouldn't be very helpful that I can think of. But we're going to get to what corresponds to the product rule and the chain rule next time. But so right now we're just going to talk about the more basic case of the addition rule and the constant multiplication rule. So the addition rule, let's start with the addition rule, which follows immediately from the addition rule for derivatives. So I'm going to go back to the capital letter notation. So if g prime of x, capital G prime of x equals little g of x, and capital F prime of x, the derivative of capital F at x, equals little f of x, then big G of x plus big F of x prime, the derivative of big G of x plus big F of x, equals little f of x plus little g of x. So stated like this is just a natural consequence of things we were talking about weeks ago. But now we can restate this fact in terms of the notation for indefinite integrals, and it will immediately give us a corollary for definite integrals. But the corollary for indefinite integrals, we can write this as indefinite integral f of x plus g of x dx equals indefinite integral of f of x dx plus the indefinite integral of g of x dx. And so this has a consequence. This immediately, via the fundamental theorem of calculus, as you could say, this immediately has a consequence for definite integrals. And the immediate consequence we have for definite integrals we can write as integral from a up to b of f of x plus g of x dx. If we wanted to think in terms of Leibniz interpretation of this is the height of the rectangle, the width of the rectangle, we could put this in parentheses to indicate this times this and be in accordance with PEMDAS. But usually we tend to be lax about that because we tend to set aside the Leibniz way of thinking about things. But as I said, of course, some people do go with that and take it to an extreme and vindicate Leibniz with their way of doing things. But we're usually going to be loose about this. This, of course, the integral starts here, the dx is here. The integral starts with this summa, and it ends with the dx, and everything in between is understood to be what's called the integrand, the thing that's being integrated. So this equals integral a to b f of x dx plus integral from a to b of g of x dx. So that's the addition rule as it applies to definite integrals, and of course definite integrals are areas, so we can interpret this in terms of areas. And so I'll give you a little example of something that might be a little bit surprising. Now this is something, the fact that I'm about to tell you predates the rest of calculus by a little bit in its development, and I mentioned the guy's name in the earlier lecture, the first lecture 1, I think I mentioned the guy's name who first observed this, but now I'm blanking on his name. He was an Italian guy, Cavalieri, who was an Italian monk. Of the Jesuit order, not to be confused with the Jesuit order, completely different. He was an Italian monk, and he had this somewhat surprising, geometrically somewhat surprising rule that you can shift things around in a maybe slightly surprising way. So, and let me say more about exactly what I mean. So I'll make these graphs smaller. So let's say this, of course, I've drawn the top half of a circle, and let's say it's the unit circle, so this is -1, and this is 1. So this is, of course, we know that this area is just pi over 2, right? Because the area of a circle is pi r squared, r is 1, pi times 1 squared, the area of the whole circle is just going to be pi. This is half the circle, so it's going to be pi over 2. This area is pi over 2, but we can also write it as integral a is -1, b is 1. So integral -1 to 1 of the square root of 1 minus x squared dx. And later on we'll get to how to evaluate this in general, because I'm sure none of you, unless you've taken this class before and remembered it very well, I'm sure none of you know off the top of your head what this is the derivative of. In fact, I don't even know off the top of my head what it's the derivative of, but we're going to get some more sophisticated methods that will allow us to integrate it. But for now, I'm just using this as an example, and we know exactly what its integral is from -1 to 1 by purely area-based arguments. So okay, I said I was going to get to Cavalieri's principle, so what is it exactly that? So it says, so this area, then let's say we have, so let's call this f of x, or sorry, yeah, this is going to be f of x is this function, f of x from -1 to 1, and then this other function I'm about to give is going to be g of x, which is also going to be from -1 to 1, and g of x is going to be, what we're going to be integrating over here is 1 plus x, so that's going to be like a triangle, and this of course has base 2, height 2, so it's going to be a triangle with area 1/2 of 4, right? 1/2 of 2 squared. So this is going to be area 4. So, okay, so everything I have so far, what am I getting at? This Cavalieri's principle. So what Cavalieri's principle allows us to do is if we add this function to this function, so that's going to give us something that might seem kind of wonky at first. It's not going to be a semicircle, but we pointwise add everything from this to this, then we're going to get this slightly funny looking function, somewhat curvy. Just maximum shifted over a little bit, as you can see by taking derivative. So this curve is 1 plus x plus the square root of 1 plus x, or sorry, 1 minus x squared. And its integral from -1 to 1 is, by the sum rule that we've just discussed, this integral of this seemingly strange shape is just going to be pi over 2 plus 4. So we can just add these areas while we're doing this slightly strange geometric operation, which is an easy algebraic operation, right? Adding two functions together is a very straightforward algebraic operation, but it's a slightly strange geometric operation. It can be a slightly strange geometric operation, but this sort of deformed thing is going to have the same, it's just going to have the sums of the areas. And like I said, this is sort of an interesting counterintuitive fact that was actually asserted before Newton, before Leibniz, before the rest of calculus, asserted by Cavalieri, 100 or a couple hundred years, I think, maybe, I don't remember the dates anymore, but it's in the lecture 1, I think. It was asserted a while before. And so this is kind of cool, sort of a geometric interpretation of something that's a slightly interesting geometric interpretation of something that's very algebraically simple. And I think that, oh yeah, one more thing, constant multiple rule. And the constant multiple rule is very straightforward, both geometrically and algebraically. Or it's pretty straightforward algebraically, I think. I guess maybe it depends how you think geometrically, but constant multiple rule. Constant multiple rule. So the integral of a of f of x, I've been using a for the bounds, let's call it c. Integral of c times f of x dx equals c times the integral of f of x dx. So now the geometric interpretation of that, say we have our semicircle again. So this is integral, so this of course, applies to indefinite or definite integrals. So this is the integral of square root of 1 minus x squared dx. So now, if we turned it into an ellipse, that would say twice as high. And of course, actually, we have this for ellipse formulas. This is not too surprising for this particular curve. But if we wanted the area now under this curve, it would just be 2 times pi over 2. So that's 2 times pi over 2. It's just pi. But of course, it might be slightly surprising that you could do this with any sort of curve. Might be surprising, might not be. I don't know. You decide. But you perform a vertical stretch by a certain factor, and that same factor applies to the area. And I guess I'm making a big deal out of it with the integral, but you could perhaps argue that similarly with the derivative, these things could be geometrically interesting. I don't know. You decide. So that's what we got cooking for today, and or what we cooked for today, and what we got cooking for tomorrow is going to be these analogs of the product rule and the chain rule, which will allow us to build up more, and possibly either tomorrow or next week we'll get to something more sophisticated, slightly more sophisticated, called trig substitution, and then there will be hyperbolic trig substitution, which is why I was a strong part of the motivation of why I introduced hyperbolic trig functions yesterday. So they're going to be useful for evaluating some integrals that at first glance appear to just be integrals of some algebraic stuff. So a final comment, actually, I keep saying that we're going to be done, but a final comment, since I'm talking about using these things for these other functions for integrals of some algebraic looking stuff. So I mentioned arctangent, but another derivative that seems algebraic at first but turns out to be somewhat trigonometric in nature is, of course, this integral. And what is this? Well, it's going to be whatever has this as its derivative. It's, of course, arctangent, tangent of x. And as a final comment to sort of emphasize or magnify something from yesterday, something from the homework. So this is integral from a up to b of this thing. Sorry, I wrote arctangent. I apologize. This is, of course, not arctangent, it's arcsine. Arcsine of x. And so if this is now a up to b, this is going to be arcsine of b minus arcsine of a. And so as you may have seen in the homework, this arcsine function, or arccosine for that matter, and you may not have bumped up on this in your example, depending on which example you gave when I asked for 2 different inverse functions, could be shifted over by 2 pi, and you'd still have another inverse function. So let's say f of x equals arcsine of x plus 2 pi. So this right here, this is another function with the property that sine of f of x equals x, as you may have seen in the homework. And it makes no difference. It has the same derivative. We could put in f of b minus f of a, and we would still have the area, and that comes from the fact that the 2 pi is just a constant factor added into the mix. Makes no difference. So this is arcsine of b plus 2 pi minus arcsine of a plus 2 pi. And the 2 pi's cancel out. We just have arcsine of b minus arcsine of a. It's the same thing. So that's just a brief comment to tie it into yesterday. And yeah, so that's it for today, and we'll be back tomorrow with the analog of the product rule, which is called integration of parts, and the analog of the chain rule, which is called use substitution.